Welcome friends to my YouTube channel Sommo Physics. On my previous lecture I told about conic section equation, that is the standard form of conic section equation, and energy of the elliptical orbits. There we have seen that the energy solely depends upon the major axis. Okay, now in today's lecture I will discuss about the differential equation of the orbit. Okay, differential equation of the orbit. So let's proceed. We know that while deriving the equation of motion of a particle in a central force field, we find the radial equation as this: m into r double dot minus r theta dot square. This is equal to f of r. Okay, so give it name, that is equation 1. Now let r, this is equals to 1 by u, that is we have to replace r by a new variable u such that r equals to 1 upon u. So what will be my r dot? My r dot will be minus 1 by u square du dt, that we can write as du d theta dt. Okay, now this is minus 1 by u square, this is du d theta, and we know that L equals to mr square d theta dt. So d theta dt will be my L by m r squared, 1 by r square, that is u square. So simply this we can write as minus L upon m du d theta. Okay, so what will be my r double dot? My r double dot will be minus L by m d2u d theta 2 into d theta dt, which means L by m into 1 by r square, which means u square. So this simply we can write as L square u square by m square into d2u d theta 2. Okay, now if we substitute all the values in equation 1, then what we get? We get m into r double dot, that means minus L square u square by m square into d2u d theta 2 minus m into r, that means 1 by u, and what is theta dot? L by mr square, that means L square by m square r to the power 4, that is u to the power 4. So this is f of 1 by u. Okay, now if we simplify it, what we get? We get minus L square u square by m into d2u d theta 2 minus L square u cube by m into f of 1 by u. So if we take minus L square u square by m common, then what we get? We get d2u d theta 2 plus u, this is equals to f of 1 by u. Okay, so finally what we can write? We can write d2u d theta 2 plus u, this is equal to minus m by L square u square into f of 1 by u. So this is the differential equation of the orbit. Okay, and this is a very important equation. By using this equation we can easily find the law of force which is given in the problem. Okay, we can find out the law of force. ঠিক আছে? Okay, so this is the differential equation of the orbit. Okay, now another thing we have to discuss about a problem Okay, so what is that problem? Now suppose a particle of mass m moves under the influence of a central force field, that is inverse square force field. So for that particle, if v is the velocity, we have to show that its velocity can be written in this way: k by m into 2 by r minus 1 by a. Okay, so k is constant, m is the mass of the particle, and a is semi-major axis. So if a particle moves under the influence of a inverse square attractive force, then its velocity can be written in this form: v square equal to k square by m into 2 by r minus 1 by a. How we can prove it? Simply, we know that total energy, this is nothing but the kinetic energy plus potential energy. Now in case of a elliptical orbit, we have already proved that total energy is minus k by 2a. Okay, now if mv is the velocity of the particle, then kinetic energy would be half mv square, and for inverse square force, inverse square field, v we can write as k by r. So just simplify it: half mv square, this we can write as k into 1 upon r minus 1 by 2a. Okay, so what would be my v square? My v square would be 2k by m into 1 upon r minus 1 by 2a. So from which we can easily write k by m into 2 by r minus 1 by a. Okay, so this is the simple but interesting problem. This is the required relation that we have to prove. So this is a simple and interesting problem related to central force. Okay, so if you don't subscribe my channel, then kindly subscribe it and share it to your friends, neighbors and relatives. Okay, now in my next video I will discuss about artificial satellite. Okay, that we will start from the next video. Okay, thank you.